Now that we understand what a force is, the next concept to grasp is what's called the moment of a force. Now, the moment of a force is a measure of the twisting effect or the torque that a force can generate by rotating about an axis of rotation. So to develop this idea a little bit more, imagine some arbitrary force, F let's call it, located on a 2D plane. Now for all intents and purposes, this 2D plane can just be a sheet of paper. Okay, so imagine the sheet of paper down in front of you now is a 2D plane. And the force F can be drawn on that 2D plane or that sheet of paper. Okay, now we imagine emerging up out of the sheet of paper or our 2D plane, we imagine a perpendicular axis of rotation. So this axis is perpendicular to the plane, and you can imagine it as almost like a pen standing up on the sheet of paper. In fact, I have a pen standing up on the sheet of paper. Okay, so my hand represents the 2D plane and the pen represents the axis about which any rotation would take place. Now, if we imagine our force as not just being drawn on the sheet of paper, but the force actually being applied to the sheet of paper, the moment of that force F about point O, the point of rotation, is how much that force is trying to twist the sheet of paper around point O or around our pen, the axis of rotation. Remember, the point about which any rotation will take place is the point of intersection between the axis of rotation and the 2D plane in which the force is located. The moment of a force is already something you're very familiar with. If you take a weight and hold it out in front of you, arm straight, that weight is applying a force to the end of my arm. And the point of rotation for my arm is my shoulder joint here. Okay, so there's a moment being generated by that force about this point of rotation, and that sort of fatigue I can feel in my shoulder as I hold this out for longer and longer is directly due to the moment that that force is generating about my shoulder joint. If I move the force closer into my body, the distance between the force and the point of rotation is reduced, and the moment or the twisting or rotational effect of that force is also reduced. If we look at our 2D plane from directly above, the axis of rotation will now be seen as a single point. Okay, now looking from this perspective allows us to identify a really key piece of information. And this is the distance between the line of action of the force and the point of rotation, or more specifically, the perpendicular distance between the line of action of the force and the point of rotation. This perpendicular distance is called the lever arm. Now, the magnitude of a moment is the product of the magnitude of the force multiplied by the lever arm. So the smaller the lever arm, the smaller the moment, and vice versa. That's why as I moved my arm closer into my body, the moment was getting smaller and smaller, and so it was easier for me to hold the weight. I can hold the weight for longer here than I can when my arm is extended out here. The weight isn't changing, but the lever arm, the distance between where the force is applied and the point of rotation, is greater here than it is when I hold the weight here. And so the lever arm is a really important piece of information that's critical to working out what the magnitude of the moment of a force actually is. When dealing with forces, we had to establish a sign convention. So, for example, we might assume that forces upwards and to the right were positive, while forces down and to the left were negative. Now, in a similar way, we have to develop a set of rules when we're dealing with moments. So in the case of moments, the distinction between positive and negative is made on the basis of the rotation that that moment would cause, whether that's clockwise or anti-clockwise. So typically we might say that moments that would tend to cause a clockwise rotation would be positive, while moments that cause an anti-clockwise rotation we might assume negative. Let's develop the idea by considering an example. Consider a force F with lever arm D between the line of action of the force and the point of rotation. If we imagine drawing a circle with radius D and starting by moving our pen in the same direction as F, the arc we would draw shows us the sense of rotation of the moment of F about the point of rotation, in this case anti-clockwise rotation. In this case we have two forces to consider. Pause the video and spend a minute to look at the diagram. Again, notice how the diagram has been set up. The lever arms in each case have been identified as the perpendicular line between the force's line of action and the point of rotation. With this information, we can identify the sense of rotation of each of the corresponding moments, M1 and M2. Now, if we think of the point of rotation as the centre of a clock face, we can easily identify m1 as anti-clockwise and m2 as clockwise. Another analogy to help you visualize the sense of rotation is to think about the force F, lever arm D, and point of rotation O as lying on a 2D plane. Let's assume the floor. If we then imagine a door hung from the axis of rotation and the force F opening the door, the swinging door identifies the sense of rotation of the moment of F about point O. Now test yourself and see if you can identify the sense of rotation in each of these cases. Pause the video now before the answers are revealed. Most of these should have been pretty straightforward. If you got a couple wrong, jump back a few slides and make sure you fully understand the explanations. The interesting case here is F. In this case, the line of action of the force passes through the point of rotation, and therefore the lever arm D is 0. Remember, moment equals force multiplied by lever arm. If the lever arm is 0, the moment is also 0. In the same way that we can consider the resultant force from a system of forces, we can also determine the resultant moment. Each of the 4 forces in this 2D force system will generate a moment about point O. Our task is to determine what is the combined effect generated by all forces acting together. Think about what you've learned so far about forces and moments. Pause the video here and spend a couple of minutes thinking about how you would solve this problem. If you think you can, go ahead and work up a solution before continuing with the video. As with any analysis, start with a sign convention. In this case, I'm going to assume that any moment that would generate a clockwise rotation about point O is a positive moment, while any moment generating anti-clockwise rotation is negative. So, one approach would be to work out the lever arm for each force in the system. Taking this route, a solution would take the form m equals minus 80 times d1 minus 60 times d2 plus 50 times d3 plus 70 times 0. Notice where and why negative signs have been used. Also notice that because the 70 Newton force passes through the point of rotation, no moment is generated. Now the problem boils down to working out d1, d2, d3, a somewhat tedious task. A slightly more straightforward approach would be to first determine the orthogonal components of each force parallel and perpendicular to the xy axis system. In this case, the geometry becomes a little easier to work with, yet the approach is completely equivalent to the first method that was outlined. So, considering each force component in turn and eliminating the 3 force components that pass through the point of rotation, the moment in this case evaluates to minus 311.1 Newton meters. And according to our sign convention used throughout the solution, this indicates an anti-clockwise resultant moment. There's an important point to be aware of here. The signs are determined only by the sense of the resulting rotation. So for example, forces pointing down and to the left are not themselves considered negative in the moment equation. Similarly, dimensions on the negative side of the xy axes are not considered negative. Remember, the moment generated by a force is the magnitude of the force multiplied by the lever arm distance. Both of these quantities, magnitude and distance, are always positive. A negative magnitude, for example, is physically meaningless. So the key point here is that the signs in the moment equation are determined by the sense of rotation alone. Okay, having seen how the last example was solved, go ahead and try and solve this one completely on your own. First, the orthogonal force components are determined. Then, each component not passing through the point of rotation is considered in turn. Be careful to observe your sign convention. It's a good idea to sketch out each force and its sense of rotation individually, just as I've done here. This way you're not likely to get confused. In cases where there are 2 orthogonal force components to consider, sum up their effects and represent the combined effect with a moment arrow. Now it's simply a matter of summing up the moments calculated along the way. In this case, the resultant moment is minus 113.2 Newton meters, with the negative sign indicating an anti-clockwise sense of rotation.